Well, hello there. So let's talk today about op-amps, operational amplifiers. The word operational amplifier is from math operations. So the operations that they're talking about here are math, like adding and subtracting or multiplying. So normally we think of amplifiers as scaling a voltage up with a gain, amplifying, making something bigger, and that's multiplication, or division if you're making it smaller. But op-amps are used for doing any kind of math on signals, normally on voltage signals. If you have to add two voltages together, if you have a sensor and it puts out two components, you need to add them together to get the full sensor value. You can't just twist the wires together to get an addition. It will do something strange there, depending on how you've wired the rest of the circuit. But if you want to add two voltage signals, you can use an op-amp circuit configured as a voltage adder and input your two voltages and get the sum of the two voltages out of the op-amp. So you can find cookbook recipes to find circuits that will do the math that you want. So if you want to add, subtract, multiply, divide, you can even do calculus. You can find op-amp circuits that will integrate a voltage or find the slope, the derivative of the voltage. All of these kinds of things are done with op-amps. So they're very powerful math operators. Anytime you want to do math on a voltage, think an op-amp. They're not high power, so if you want to drive a big speaker or a motor or something like that, that's a different kind of amplifier, a power amplifier that can provide enough power. Op-amps are very small normally, as you saw in the lab, and they don't provide very much power. So hopefully you remember op-amps from Circuits Lab, where we used this 741 version of the op-amp and did some basic amplification experiments. So we're going to move forward and focus on the theory of op-amps for these lectures. Here is the op-amp chip that you used. It's an 8-pin DIP package, and op-amps come in many different chip formats. So there are just 3 pins and the power supply that we have to hook up somehow. So some chips have more than one op-amp, some have a single one like this one. An op-amp has 2 inputs, the positive input here with the plus and the negative input there. This is called the inverting input. This is called the non-inverting input. So positive is non-inverting, negative is inverting. My little joke is that non-inverting is a double negative, so the positive terminal there should be a verting input, but no one ever does that. So to use an op-amp, you need to supply power to the supply pins that are shown here in blue, and that is what's feeding the output terminal. That comes from these supplies, and the voltages here, plus VCC and minus VCC, limit how much V out can be. So often you'll put like a plus 12 volts here and a minus 12 volts there, and then V out can swing between a little below 12 volts and a little above negative 12 volts. Normally this minus VCC is not ground. That would be called a single supply circuit, and normally this is actually below ground. It's a negative voltage. So if your V out here is stuck at a voltage that doesn't seem to match the equations from the op-amp, make sure you have enough supply voltage to the chip. For the theory side of things, we assume that the plus and minus VCC are plus and minus infinity, and so that V out is not limited by any sort of power supply, and we don't show these terminals normally for a theoretical circuit. So it's important to realize the op-amp isn't a single monolithic kind of component. It's actually made of a lot of transistors and resistors and then capacitors. This is a circuit diagram from the 741. So it's a circuit that is created. It's not a single thing like a capacitor or an inductor. The big thing with op-amps is there is this really high gain, a high voltage gain. The equation that governs how this works is the output voltage here, V out, is the gain. Gain is just a word for a multiplier, times the difference between the non-inverting and the inverting input. So Vp here on the non-inverting Vn here on the inverting input. If you subtract those two and multiply by A, that's what you get for the output voltage. And the thing is, this A is really big, usually around 1,000,000, and that's called the open loop gain. And we usually build these into a circuit that have a different gain dependent on some resistors and things. So be careful when you're talking about gain. We very rarely talk about the open loop gain, this A here, but it is how op amps work. And you can see the V out versus the difference. It's linear until it saturates based on your supply voltage, positive and negative. I think you did some experiments in the circuits lab to see that. Here's an equivalent circuit. So this isn't how you would build an op amp, but it's a nice way to model it. So the model is that we have a voltage controlled voltage source right here, and it uses this equation, A Vp minus Vn, and that gives us the V out. There's an output resistance here to make it seem realistic, and then the two input terminals are connected by another resistor here. If we do that, we can model all the parts of the op amp. To make this an ideal op amp, A, which is normally in the range of about 1,000,000, we would call it infinity. Internal resistance, Ri here, is normally large, again in the mega ohm range, call that infinity. And the output resistance here, normally we want to be very low. It's usually in the ohms, a few ohms, and we assume it would be 0 in an ideal op amp. So this is a way that we can model an op amp circuit and include some of the non-ideal things, but this model is a little more complicated than we actually need. We're going to see a simpler way to do most of our circuit analysis with op amps. So remember this, but it's not our primary way to analyze the circuit. So here is a way that we don't use op amps very often, but it's just using the direct open loop properties of the op amp. So if we have an op amp here with a 12 volt and a negative 12 volt supply, Vn is connected to ground, and there's a resistor and an LED connected opposite to each other. So if VO is positive, then the red LED is going to light. If VO is negative, then the current's going to flow from 0 volts to the negative voltage, and the green LED would light. And the LEDs won't light up if the current's back or the voltage is backwards for them. So if we look at this with 2 volts at Vp, Vn is 0 volts, then Vp 2 minus 0, we have 2. We multiply that by A, call it 1,000,000, and we should see 2,000,000 volts on the output here. So we're not going to really get 2,000,000 volts. It's going to saturate because the maximum it can put out is 12 volts. So you'll get 12, maybe 10, depending on the op amp. Some op amps go right up to the power supply, and some have a little bit of a voltage threshold that they're a little bit below. If we set the non-inverting input here to negative 2 volts, then we have a negative 2 minus 0. So we have negative 2 times the gain of 1,000,000, and we get negative 1,000,000 volts. So again, we're not going to see negative 1,000,000 volts. It's going to be saturated at the power supply level on the low side here. So we're going to see around negative 12 volts. So with negative 12 volts, the green LED would light up. With positive 12 volts, the red LED would light up. And so this is with just about any positive voltage, this will saturate fully. And with any negative voltage, this will saturate fully. So it's a switch. It's either on or off. There's a small range where you're in the millionths of volts that it's in between. But for any practical sense, to 6 decimal points or so, this is either on or off. So again, this isn't a conventional way, but it is a way that works for op amps. So this is a more typical circuit for an op amp. We have the output connected with a resistor back to one of the inputs. And that's feedback. We're feeding the output back to the inputs. And that's how op-amps are almost always used, with a feedback circuit. So we have a source voltage here connected to the non-inverting input, the plus terminal. We have the junction here between these two resistors fed back to the inverting input, the minus terminal. And we're trying to figure out normally what is the output voltage given this supply voltage Vs. So we can do Kirchhoff's law. We have a voltage-controlled voltage source, and we've got a resistor. We can just do node analysis. So at this node here, we know that we've got V out at node A, and over here we have this voltage-controlled voltage source. So the I4 going out is VO minus the voltage-controlled voltage source equation divided by R0 Vn, because we've got it here, minus VO, that's coming in, divided by R1 equals this current going out. So over here for this node, we're going to go from B all the way back to this node at P. So Vn minus Vp over Ri, that's this one. Vn over R2, that's this one. Vn minus V out divided by R1, that's this one going out. So these two Kirchhoff's current law equations we can solve. Here they're solving for V out divided by Vs. And written out, it's this big long equation. And A is large. A is usually around 1,000,000. So if you put in an A of 1,000,000, we can come up with this gain. The ratio of the output over the input is the gain of 4.99975. If we use the ideal op-amp models where A is infinity, then, sorry, the ARI and the ARI here cancel. The rest of these terms are negligible. So we get R1 plus R2 divided by R2 for the gain here, which is 5. So you can see for our ideal op-amp, the answers are almost the same. So we normally use these ideal op-amp models because it's much simpler, as we'll see. But this works. So this is the circuit gain. This is a circuit gain of 5. So V out divided by Vs is 5. So V out is 5 times the input voltage Vs. So this is feedback. Again, we looked at it in this last example, feeding some of the output back to the input. That means if this gets really big, if this is 1,000,000 volts, then you get some of that voltage back here, and since it's Vp minus Vn, as Vn gets bigger, A gets smaller. So if this is big, the voltage out here, it makes this big, which makes this small. So it's a way to control some of the large swings. So we take some of the output, feed it back to the input. Negative feedback decreases the input signal, and it makes it work. We assume a gain of 1,000,000 for A, capital A here, but in fact they'll sell the op-amp if it's in a very wide range, so it makes it an inexpensive part because it works fine if the gain is 1,000,000 or 2,000,000 or 10,000,000. It doesn't have to be precise, it just has to be big, and it will work. So again, here is the ideal op-amp with infinity open loop gain, infinity input resistance Ri, and 0 output resistance R0. If we have those ideal op-amp conditions, then we can find these golden rules that we use, and these are what we use for practical op-amp analysis. So remember these, keep this handy. The two rules are the golden rules according to these slides, but also called the summing point constraint. The first rule is that Vp, the non-inverting input voltage, equals Vn. So that's because the gain is infinity, so any difference between these makes infinity volts come out, and we feed that back, and so that drives these to be the same. So the two inputs are always going to be balanced with an ideal op-amp that has a feedback circuit. The other rule is that the current through the inputs here, IP and IN, those are going to be zero. No current into the op-amp because the input resistance is infinity. We don't say that the current coming out is zero. The current coming out is really unknown. We don't have an Ohm's law or anything we can use. So we can't do Kirchhoff's current law at the Vout pin because we don't know the current coming out of the op-amp. So we don't apply Kirchhoff's current law at the op-amp's output. But we can do it here and here, and with these equations we have enough equations to solve the system anyway. So with these two equations and node analysis we can solve any op-amp circuit. So let's try that. Try using those rules, and this is how we're going to go forward for all of the homework. We're going to use these golden rules or the summing point constraint rules and analyze the circuit. So you have to check that it has feedback, but here's our op-amp. We've got the non-inverting input on the bottom and the inverting on the top, so make sure you pay attention where the plus and the minus are when you're wiring the chip, because it makes a difference. And we've got an input voltage Vs, Rs, and Rf. So RL is the load resistor that we're driving, but this is the feedback resistor, and this is the source that goes with Vs. And we're trying to find Vout. We usually want Vout as a function of the input voltage Vs. So we just do node analysis, start with the inputs. This one, the non-inverting input, is connected to ground. So Vp equals 0, which means Vn equals 0 from one of our rules. If we do the Vn node, we have no current this way, In. I2 going out is going to be Vn minus V0 divided by Rf. It's this one. Here's our In. And the current here is going to be Vn minus Vs divided by Rs. So these three terms are the current at this node. This one is 0. So we can use these rules. Vn equals Vp, that's the rule. And here in this one particular case, it's not always true, but Vp is connected to ground. So this equals 0 isn't the summing point constraint, but Vp equals 0, and so Vn has to equal 0 as well. And that is the summing point constraint, that these two are equal. The other rule is that In equals 0, so this term drops out. So if we put zeros for Vn and 0 for In, we can solve for the output voltage V0, and it's negative, remember there's a negative here, Rf over Rs, so the ratio of these two resistors times Vs. So this is what we normally want to do. So it's node analysis with our two rules. This is called an inverting amplifier because if Vs is 5 volts and Rf equals Rs, then the gain here would be -1. So if you have 5 volts input, you'd have -5 output. If this is positive, the output is negative. Sometimes people don't like that, but it works fine for things like audio amplifiers where you're just doing a sine wave. And it's a very simple circuit that only takes 2 resistors, so it's always the one we start with. The gain here can be anywhere from 0 to really large numbers, but it's always going to be negative. So this is the way we think about these amplifiers, is they have a gain. So Vout is negative Rf over Rs Vs, that's what we solved before. So the gain here is negative Rf over Rs, and Vout is G times Vs. G is defined to be the output voltage divided by the input voltage. So often you'll see in a data sheet or a cookbook equations for the gain in terms of the resistors. Alright, so let's check another circuit. So this is a different op-amp circuit. You can see we have the non-inverting input on the top now, inverting input on the bottom. We've got 3 resistors, R1, R2, and Rs. So it's a different circuit. It's going to have a different equation for Vout. But we do the same process. We do Kirchhoff's laws, node analysis, starting with these input nodes normally, and trying to see what we get for Vout. So at the Vn node here, no current flows on this branch because that's one of our rules. And so Vn, we've got Vn minus 0 divided by R2, Vn over R2, and Vn minus Vo over R1. That's this one. So this going out plus this going out has to equal nothing going in. That's our first equation, that node. Then the P node here, again, no current going into the op-amp. So the current going the other way on this node would be Vp minus Vs divided by Rs, and that has to equal 0 using the golden rule, the summing point constraint. So that tells us that Vp equals Vs. Vp here equals the same as Vs, and with the golden rule or summing point constraint, Vn equals Vp. So this has to be Vs from Kirchhoff's current law, and this has to be Vs from the summing point constraints. So we can put Vs into our equations up here for Vn, and then solve for the output voltage in terms of the source. So plug that up here, and you'll find Vout is R1 plus R2 over R2 times Vs. And normally we write this in terms of the gain of the system, which is the ratio of the output over the input, is R1 plus R2 over R2. Here the gain is always positive, so if you have a positive input voltage, you get a positive output voltage, which is handy for a lot of things like sensors. But the gain here always has to be greater than 1, because we always have an R2 in the bottom. So the smallest you could have this gain be, if you had R1 was a short circuit, 0 ohms, you'd have R2 over R2. But it can be larger. So normally gains tend to be greater than 1, and so then we put R1 plus R2 divided by R2 for the gain. So this is the non-inverting amplifier because the input and the output have the same sign on the voltage, and it's a very common one too. It takes 3 resistors to make this one versus 2 for the inverting amplifier, and they're probably the most common circuits you'll see with op-amps. Okay, so next up we will have more examples of op-amp circuit analysis. It's really important. Sometimes people see op-amp and they just want to use one of the equations that we just saw for the circuit. But remember, there are many, many op-amp circuits, and you have to look at the circuit and do the analysis, or look at the circuit and find it in a book to see what the equations are for that particular circuit. So pay attention to the circuit and how it's laid out. We have the non-inverting right now. If you see the inverting input connected to a voltage divider, 2 resistors in series, or if you see the non-inverting input connected to ground, that's could be our inverting amplifier. So pay attention to the layout when you're doing the analysis.